Good morning. Welcome to our talk. If you're expecting a talk about sci-fi robots with lasers, it's the wrong talk. We're talking about real-world systems here, ships, planes, cars, where one bad line of code can cause real physical harm. And that, in our world, in the transportation world, critical infrastructure, that's not future risk. It's already here. So yeah, the title's a little clickbait, but the problem is real. When most people think of cyber threats, they think hackers, ransomware, phishing, and those are real concerns. But in the maritime industry, there's a Trojan horse creeping that doesn't get enough attention. That's software quality and engineering practice. So in maritime, we're racing towards more automation, more digitalization, more connected systems in ships and ports. And that's great for efficiency until the code driving those systems is flawed, misunderstood, or poorly tested. And unlike a hacker, bad code doesn't have to break in. It's already inside, running exactly as written, even what if what it's written to do is dangerous. So who are we? A little bit about myself. I'm Michael DeVolld, Director of Maritime Cybersecurity at ABS Consulting. Been in maritime my whole career, started on the deck plates as a technician working on ship systems, navigating ships, transitioned into inspecting commercial ships, doing investigation on major maritime casualties such as Costa Concordia, the cruise ship that sank off the port off the coast of Italy. And so through my career, I've seen real incidents, people dying, major environmental disasters, transitioned into cyber about 10 years ago and been working at the nexus of marine operations, engineering, compliance, and policy and how that connects to cyber risk. Co-presenter is Austin Reid.
Good morning, everybody. My name is Austin Reid. I am a senior consultant with ABS. I've been in the maritime industry for 10 years. This is my fourth DEFCON. I've started in cargo operations as stevedore superintendent and then moved into automated container terminal operations. So I was able to see kind of the old school way of moving cargo and then the bleeding edge side. So it got me passionate about how finding ways to secure control systems, and grateful to be able to work with Michael and the team here. So looking forward to more of the presentation.
All right, we have to give an acknowledgement to our good friend and colleague, Chris Stein. We weren't sure if he was gonna make it, but he made it across the pond to be with us today. So Chris is one of the most brilliant engineers I've ever had the pleasure of knowing. He's actually worked in developing and maintaining some of these systems that we're gonna talk about today. So we're happy to have him here. We're gonna bring him up to talk about a really cool simulation video that he produced. You wanna say anything, Chris?
No.
Okay, all right. Okay, so what is cyber today? Is that this endless wall of logos promising to save you from the scary thing of the week? You know, in 2025, the buzzwords are all the same: AI, nation-state hackers, APTs, hyperconvergence. If you throw in AIS, you have yourself a maritime keynote. So what's the problem? It's a lot of noise, and while folks are out there chasing hype, the boring stuff like bad software and critical systems, poor engineering practice, quietly is waiting to cause real-world damage. And that's what we're here to talk about. But before we go any further, let's all agree on the definition of a computer. To the layman's, you talk about a computer, it's what's on the left, that's a desktop PC. But in reality, a computer is anything with a processor, memory, and the ability to execute code. That's your key fob, your smart lights, your watch, your gaming consoles. In the maritime world, this includes your navigation system, your engine controls, your balance system, and yes, even the coffee machine on the bridge. But if it runs code, it's a computer, and that means it can fail, it can be hacked, or it can be programmed badly from the start. Which brings us to ships. So on ships, these computers aren't just laptops in the captain's cabin, they're embedded in every single critical system. The diagram on the top there comes from IAC standard E22. If you're working in maritime, if you're interested in maritime, read it, know it, love it. This is a great standard. At the top, you have a vessel. And beneath it are systems, subsystems, programmable devices, and at the heart of every one of those systems are software modules running inside. So down at the bottom, a few key examples: PLC that controls automation, pump moving critical fluids, variable frequency drive adjusting motor speed. You got your flow meter measuring critical fluids, and engine telegraph that tells the main engine how fast to turn. The point is, every one of these depends on software, If the code is wrong, misunderstood, or compromised, that system will still do exactly what the code tells it to do, even if it's dangerous. So a little example. This is how we went from dumb but safe to smart but hackable. So on the left, that's an old school wax pellet thermostat. No IP address, no firmware, no updates, no 0 days, just heat in, valve out. Basically, it's the air gap solution of engine cooling. On the right, modern PLC-based control system. You got your sensor, you got your logic controller, motorized valve, and probably a web interface with the default password set to admin. It's brilliant for precision. You can set custom temps, you can log everything, and probably control it remotely from your couch. But what's the trade-off? That solid hunk of brass is now a fully fledged cyber attack surface. Congratulations, your thermostat is now part of the Internet of Targets. So what's the bigger point? We replace mechanical systems with networked ones. We're not just upgrading capability, we're importing risks. So let's talk about what that means for cyber. So what does replacing mechanical thermostats with a networked device matter to cyber? Because we're in the fourth industrial revolution, cyber is everywhere. We've moved from steam and mechanics to mass production, computerized automation, and now to cyber physical systems where the physical world is tied directly to code and networks. This means a change in logic. A bug in a code or a compromised sensor doesn't just make the screen flash red. It can make real-world equipment move, fail, or break in dangerous ways. And it's not always about elite hackers or exotic malware. Sometimes software quality is just poor. Developers may not understand process limits, control systems don't protect themselves or protect themselves from the user, and hardware failure is not accounted for, which leads to unpredictable and sometimes catastrophic results. If you think that's theoretical, look at the headlines. These aren't just hypothetical. Software bugs have been killing people and breaking hardware for decades. Boeing 787s ground by a power bug, an F-35 lost because of bad code, NASA's $327 million Mars orbiter gone over a metric imperial mix-up. Toyota's killer firmware, a divide by zero that stopped a Navy ship dead in the water, the Chinook helicopter crash tied to unsafe code. The point is the system will do exactly what it's told, even if it's the wrong thing. When code controls the physical world, mistakes don't just crash programs, they crash planes, ships, and cars. So we talked about theory. Let's watch it happen. I'm going to bring Chris up to talk about a video he made of a simulation. Enjoy.
Thanks, Michael. Hi, everyone. I'm Chris. That doesn't work very well in the way that it's configured, so let me just see if I can fix it. If not, I will try to talk to it. The video is very, very interesting, so I really want to show it to you. So let me just try to get it up on screen. Oh. I got a conference center full of IT people, so no wonder we couldn't get this to work.
That's actually video in my downloads folder. I'll play it straight from the file.
Oh, no.
Oh, I got it.
This is all right. So I know this is a little bit unclear. I'm just going to start it and start talking through it. This is a simulator. That simulator is made by Kongsberg, one of the leading machinery automation system makers in the maritime industry. The simulator that we're seeing here is based on a ship called the Viking Grace. And why that's important is because the Viking Grace is a RoPax, meaning a ship that takes both cars and passengers that sails from Stockholm to Finland, to Turku. It also means that it sails through the archipelago in Stockholm as well as in Turku about 60% of the time at sea. So it's really, really unclear here. So let me just pause it for a second and tell you what it is that we're seeing. What we're seeing here is the ship's power management system. This is a visual indication of how the engines are doing, how much power that we have, the producers and the consumers. Right now, we're running on 4 engines full ahead. And the specific configuration for the ship is that we're running all 4 engines at about 50%. And the reason for that is, as I said, we're sailing in the archipelago. If we have a blackout, we risk sailing into a rock. So therefore, the ship operator, which is Viking Line, has decided that having spare power is really important in this scenario so we avoid a situation like the Dolly up in Baltimore. What I want to talk about here is it's not a cyber thing per se. It relates to what Michael says, but it also talks a little bit into about how we can engineer ourselves out of some of these software problems without actually touching the software. It's really, really bad like this. Yeah, sorry about this, folks. Really, really, really bad. Actually, I'm just gonna pause it, and this is more fun when you get to see it happen in the video. However, I can't really do that. This is the ship's automation system. The ship's automation systems allows us to remotely control things from the engine control room that are located down in the machinery space. In this particular case, what we're looking at here are two of the generators, the diesel generators that we have on the ship. These generators are being cooled by the seawater cooling system, which then exchanges heat with the freshwater cooling system, that then exchanges heat with the freshwater cooling jacket that's in the engine itself. The water that is circulating in the engine goes from the freshwater cooling jacket in the engine into a heat exchanger. That heat exchanger is what you see right there. And the valve that we have right here is the one where you set the set point for when the water is diverted into the heat exchanger. Now, that set point right now is about 70 degrees. But because it's digitally controlled, we can change it to whatever we want. In a scenario where software fails, like Michael talked about, we can actually cause a blackout on the ship just by manipulating that set point on all four engines. Because the software is identical across all four engines, but it's one big automation system that controls this specific valve, we will risk that any incident that will disrupt, let's say, that set point will propagate across all four engines. So in this video, my spiel is normally a little different when I can actually show you the video with a higher quality, so forgive me for being a little bit inconsistent here. But what we're doing here is we're manually setting the set point to 700 degrees. And the reason we're doing that is because we want to see what happens when there's a software failure that actually makes that valve stick because of software, not because the valve itself is stuck. The shocking part here is not that the set point can be changed. Of course it can be changed. Software can fail, you can do it manually, somebody does something, whatever. But what actually happens when that temperature is set to a temperature that's higher than the shutdown temperature for the engine? Now, let me see if I can pull this out to the right a little bit. So you see the second counter up there. We started the simulation at 38 seconds. Now we're simulating the ship is running full ahead on these four engines. And one thing that I want you to notice is how little time it actually takes from the point where we made that valve stick till we actually start seeing problems. And I'm going to be a little bit silent for a few seconds here, but it's not going to be long. The tension is rising. There. Now we're getting the first warning that the temperature on the outlet of the freshwater jacket is high, meaning that the water in the engine is coming up to a temperature that it's not supposed to be at. We already got the first shutdown pre-warning, and in just a few seconds here, we got the first engine that tripped. The second engine that tripped, the fourth that tripped, and the third one, the breaker already tripped there. So in less than 90 seconds, a manipulation of the set point can cause a complete ship blackout. That's the video. So what actually happened here, oh, sorry, I forgot about this problem. I'm not that smart. We're doing this. Oh, by the way, all the alarms that we saw, all the red and yellow little lights that were blinking, there are about 600 to 800 alarms that pop up when this happens on a ship. You have no idea what's going on. You have to sit and scroll through all these alarms to find out what is it that happened. Can I actually figure out that it's the set point that was manipulated, or is it something completely different? So we've seen cases where that has actually impeded some of the investigations, the live investigations on the ship, which has caused catastrophic scenarios. I will mention the Viking sky as one of them if anyone knows what that is. So what really happened in this scenario, just to go over it really quickly, is something manipulated a set point. It doesn't matter what it is. We don't need to talk about hackers. We don't need to talk about software failure. What matters is we had a situation where a set point was manipulated. This is just an example. It could be anything. We could turn off the compressors and the oil mist detection would fail and it would cause the same scenario. We had no circulation through the heat exchanger. That means that the engine is overheating. We didn't even touch the engine, but because we touched the cooling of the engine the emergency shutdown for the engine tripped the engine, which led to a blackout and loss of propulsion. Technically, we've now sailed into the rock. And with that, I'll give it to Austin.
Almost done. Got another 2 minutes. All right. Bear with me as we scroll down. Okay, I am going to, just for the sake of time, move a little faster through these last couple slides. So here we wanted to go over kind of the example of the Boeing 737 MAX MCAS system. There's a lot of wonderful, really smart folks here in the front row from the Aerospace Village that can tell you more about that. So I'm going to jump right into the maritime specific examples. So Michael had mentioned earlier about how there was a divide by zero incident aboard the USS Yorktown. So this is a cautionary tale. Basically back in the late 90s, the Navy thought it would be a great idea to digitize shipboard systems. Windows NT everywhere. It was sold as a future, more automation, fewer crew, streamlined operations. And then they realized, they realized that they had gone a little too far. One of the crew members set a valve set point to zero. There was a set function in that system that then divided by zero, crashed the system, and the ship systems were offline for about 2 weeks. So there's a great kind of caveat there. You can't see that, or a quote there from Admiral or Alexander Krekich, basically saying that talking about the benefits of automation without having backups, and then next slide over basically shows that there's a casualty on the systems there. So let's go to the next slide. So this is the part I'm pretty passionate about, is the risk of essentially what vibe coding has brought to critical systems. This is basically adding in today's development culture of rushing things and trying to not actually understand your critical systems. So shipping and maritime industry is very legacy and very basically a laggard sector that does not adapt to change very well. So we've seen folks that will basically be working to develop WinZip one day and they could be working on propulsion control systems the next day. So when we have folks that are relying on AI tools or anything like that, we're starting to see an enshittification, to borrow Cory Doctorow's quote, of code bases. So I worry that this is going to trickle down into what we'd see in basically the development of critical systems. So if we start relying on just bad code base and bad code practices, we could see a lot of other systems or a lot of other examples that Michael and Chris talked about today reach more into the maritime industry. So that's kind of the concern that a lot of us are worried about. And I just, the enshittification is what I see is an apt term for it. You can't just uninstall and go back to brass valves and wax thermometers. If something goes bad, you're stuck with that fragility, and there's not necessarily a lot of backups engineered into that as we start layering emerging technology onto the legacy systems. So is this enough? There's been a huge push towards our new emerging regulations from the international community on cybersecurity regulations from the IX committee, so International Association of Classification Societies. As Michael mentioned, everyone in this room, if you're interested in maritime, go read E26, E27, and E22. They are where everything's moving towards, but specifically on E22. It is basically applying IEC 62443 SL1 control base to the maritime sector, and it is trying to drag the maritime sector into a secure by design process for new builds. So when you layer that momentum of the regulatory bodies pulling the industry forward on top of vendors and providers and business use cases of stacking, IT equipment into critical systems, there is a worry and concern there for failures, whether that's unplanned or result of adversarial activity. So next slide. Actually, going to jump down to. Yeah, so basically, if you take nothing else from this talk, I would say that the biggest risks in maritime aren't from external hackers. It's from the stacking of emerging technology on top of legacy systems with bad code and bad processes and lack of control. So we've seen it in aviation, we've seen it in Navy, we've seen it with the shipping industry. It's just a matter of time before more instances and examples happen. So it's, I would say, the vendor magic sauce until it's so fragile that a single bad variable misread sensor can take down an entire vessel. That's Cory Doctorow's enshittification in action, except instead of running on social media sites, it can ruin a ship or take lives. So I'll end there. Appreciate everyone. Thank you for going to